problem with virtual reality is that the physical area is constrained to the size of the tracking area. There are many techniques used to circumvent this problem, commonly referred to as redirection techniques. One technique involves rotating the user more or less in the virtual world than in the physical world. This technique is referred to as rotation gain. Psychophysical experiments conducted by Frank Steinicke and Evan Suma sought to uncover people's ability to detect the usage of rotation gain. Steinicke's test indicated that the test participants were not as good at detecting the use of rotation gain as the test participants in Suma's test. This project has investigated how some variables affect the perceivability of rotation gain in psychophysical experiments in virtual reality. Test 1 sought to uncover if the difference between the virtual environment used in Steinicke's test and the virtual environment used in Suma's test could be the reason to why Steinicke's test participants were not as good at detecting the use of rotation gain as the test participants in Suma's test. The results of this test indicate that changing the virtual environment only influences test participants' ability to detect rotation gain in very extreme cases. In other words, it does not seem likely that the difference between the virtual environments used in Steinicke's test and Evan's test was the cause of the difference in their results. Interestingly, our control scenario, which was almost identical to the scenario used in Suma's test, was perceived differently by test participants in our test compared to Suma's test. Test participants felt that their movement was slower in our control scenario than in Suma's test. Since our test was within group, we believe that the reason was that the other scenarios affected the control scenario. Test 2 sought to investigate if this was really the case. Isolating the control scenario and one of the scenarios from Test 1 resulted in the control scenario being where it was in Suma's test. This clearly indicated that the scenarios from Test 1 had affected the results of the control scenario. To sum up, Test 1 and Test 2 indicated that the virtual environment needs to be dramatically changed to affect the test participants' ability to detect rotation gain, and the scenarios affect each other if they're tested using a within-group test method. Test 3 was a broader test, combining a test of how the system latency and test of how the field of view affects test participants' ability to detect rotation gain. System latency was artificially added to produce the effects of 0.5 and 1 second latency. Test participants got worse at detecting rotation gain as the latency was increased. However, the latency of Steinicke's virtual reality system was not that high. In comparison, the system we used had an inherent system latency of approximately 0.1 second. The second test of Test 3 sought to uncover the relation between the field of view and the test participants' ability to detect rotation gain. The field of view was decreased to simulate a field of view that was a little smaller than in Steinicke's test. Also, an extremely small field of view was tested. Both the field of view that was slightly smaller than the one used in Steinicke's test and the extremely small field of view actually performed a little better compared to the full field of view, although using the extremely small field of view caused the test participants to generally perceive the virtual world as moving much faster than in the other scenarios. To sum up, decreasing the field of view seemed to improve test participants' ability to detect rotation gain, while decreasing the field of view extremely causes test participants to perceive the movement as being faster in general. The project successfully investigated some relevant variables in rotation gain experiments, but could not determine why there was a difference between test participants' ability to detect rotation gain in Suma's test and Steineck's test.